So I took this doubling every year and extrapolated it 10 years from 1965 to 1975 from 60 components to 60,000 components on a chip.
To telling us, yeah. Guys, we've been giving you a free ride for 30 years while you
Extrapolated it 10 years from 1965.
All right, good afternoon, everyone. Sorry for being late. Well, there are obviously some kind of technical issues on my side. So, since the pandemic starts, we start to move all the classes online. And it turns out that I feel like every time when I teach a lecture, I'm like the main character in Assessing Classroom. If you haven't seen this one, that's a really good one. You should be able to find it on Netflix. So the thing is, like, every time I have to deal with so many devices, and sometimes some of them will work, some of them wouldn't. And so just for now, I've just figured out that my audio device has some issues. So to give you the better quality, I just let you know, like, there are tons of things happening behind the scene. So, but behind the scene, there are things that you should know. There are things that you shouldn't know. But there are definitely one thing that you should know regarding computer architecture behind the scenes. So first of all, well, Nick, do you have a question?
Yeah, I'm just curious, because last summer session, my class, we used AutoGrader. I'm just curious why we're not using AutoGrader.
Well, we are just not using AutoGrader.
Oh,
okay. All right. So, so for the von Neumann architecture, so the very basic important things regarding the computer architecture is that you just remember every computer is a von Neumann computer, which consists of a processor and memory, and the memory should store data and instructions whenever you need to execute the program. It has to go through every instruction and access data whenever it's necessary. And because we have to go through every instruction, so the CPU performance, which is defined by the reverse of the execution time, meaning that the better performance means shorter execution time. And because of that, so your performance is basically defined by the number of instructions that you have to execute for the program and how many cycles per instructions on average, as well as the cycle time for your processor. So that's how we define the performance. And previously we mentioned that for the speed up, the only definition is that if we want to say y is n times faster than x, you should have it as execution time of x over execution time y. So if I have a new design, well, I want to say the new design is faster than the old design by whatever times, it should be calculated as the execution time of the old design over the execution time of the new design. And so you can see, like, there are basically three important factors in computers performance, and programmer is the only factor that can affect all things within the computer performance equation. So that's why you guys are important. So at the end of the last lecture, we talked about m-DOS law, which means that the speed up is 1 over 1 minus f plus f over s. And f means the fraction of time in the original program, and the s is the speed up we can achieve on f. So some of you might think it's a different definition of speed up, but if you look m-DOS, if you think m-DOS in this way, it's actually rescale your original execution time into 1. And so in this way, if I have f portions of the program can be speed up by a factor of s, then the new execution time will be f over s plus 1 minus f. So the enhanced speed up will be 1 over 1 minus f plus f over s. And we also say that for MDOSLO, you can apply it on multiple optimizations. So for today's lecture, we are going to continue our exploration on MDOSLO, and I'm going to tell you about like how to make a fair comparison among different computer architectures. So before we start the rest of the discussion, I definitely want you to practice MDOSLO again. Make sure that we can move on. So why don't you practice this one, and maybe we will need a discussion later. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, I just figured out that we have gone through this question in the last lecture, and the right answer for this question it should be 17. Okay, so right now I am having an extended question for you on MDOSLO. So let's try this extended question for MDOSLO, which require your understanding about multiple optimizations. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according what I learned from you guys, it looks like, well, you know, both B and C, they are popular answers. So it definitely means that we need some more discussion on this. So I'm going to use the breakout room for you guys to discuss. And well, I already sent out the question so through the group chat. So use that for discussion, and we will synchronize our result in about 2 minutes. Go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so the most popular answer right now is C, but I do want to make sure that you chose C is not because most of people chose C. So can I have some of you explaining how you derived the answer that your group selected? Well, if not, then I would probably ask for, what do I have? Kevin, what do you think? Or what does your group think?
Most of our group wasn't really sure.
But what do you guys think?
I guess most of us put C, but like we couldn't get a concise answer.
Okay, but what do you guys have in mind? So let's begin by this, right? So this is N-DOS law, right?
Yeah.
So tell me what's the form of N-DOS law?
What?
What's the form? What's the formula of N-DOS law?
1/1 minus F plus F over S.
Right. So what's the result we want it to be?
We want it to be 2 times faster.
We want it to be 2 times faster, right? And what new memory technology that replaced flash memory that serve as the storage device? Like, well, it says the system spent like 16% of time in accessing the flash, right? So if we want to use something to replace the flash to achieve twice speed up, how much faster that speed up needs to be? So what's the F here should be?
Point 0.16 or
Yep, 0.16, 16%, right? So this S is the unknown that we have to resolve, right? So given that, right, you will have an equation like this, and then you will figure out this x is smaller than 1, which is not really something that m also can be bounded to, right? So none of the above is the answer, right? Because it seems like we have a new memory technology, but it tells us that you want a new memory technology to be slower. So this doesn't make sense, right? So none of the above is the answer. Okay. Okay. So Danling, question.
Yes. So what is the overhead here?
So the overhead is the software overhead, means the time you spend on the CPU code.
Okay, I see.
Yeah, so I think I mistakenly skipped the previous question, and that's actually one thing I wanted to do now. So this question, like we said, Final Fantasy spent 95% of the time in accessing hard disk drive, and that was the part that we have in the last lecture. But right now we are saying that with we want to replace the hard disk drive with flash, which give us 100 times faster access time and better processor to accelerate the software overhead by twice. So how much can we speed up the map loading process? So if you don't mind, do you guys mind to, if you don't mind, can you like go back to this question again and let's have a group discussion on this question, because I just figured out that most of you didn't get the answer right in a boat. So why don't we just like do this question again? I just set out a screenshot of this question. So let's do it now. let's wrap up in 5, 4, 3, 2, 1. Time is up. Okay, so right now, well, we have a split. So half of you think it's C, half of you think it's D. So can I have some of you sharing what do you think? Like if you think it's C, how do you get your answer? If you think it's D, how do you get your answer? Okay, so I have Danling. How did you solve this?
So I remember from last lecture we had a similar problem, but we didn't have the overhead by 2 times faster, I think, that part. So from the previous lecture, we just plugging into the formula that
Okay,
F
so how the
is,
formula should look like?
so it's gonna be 1 over 1 minus 0.95
Okay,
plus
0.95 plus
plus 0.95 over 100.
0.95 over 100, right?
Right.
So that's the, and what else? What else? Is that good? So for, is that good?
Well, but like for our current question, I think I just picked up the answer you just went through. It was 29 times faster.
Right, but
So
this answer, is this going to be 29?
no, this is gonna be 17. So
Right, so
I
how
think
to make it 29? So here's the thing, right? This question is actually an example of multiple optimizations, because this question is saying about 95% of time is accessing the hard disk drive. The rest, the rest of the time, that will be the software overhead for the 5%, right? So for the 95% of the time, we speed up by 100 times. For the 5% of time, we speed up by twice. So that would give us the 29 times speed up. Okay, Byron, question?
So I guess like a easy way to remember disjoint MDAL optimizations would be to divide each portion by its speed up.
Yep.
Because
And
the speed up would
make
be,
sure that each portion, they must be disjoint.
yeah.
Okay. Okay, so that will be MDOS law. So let's go back to the, okay, so sorry, I accidentally skipped this question because this is actually a very exemplary question on multiple optimization. So for this question, you have to use multiple optimization because we have two parts that get speed up. For the 95%, it gets 100% speed up. For the 5%, it gets twice speed up. So the synthetic result will be 29 times. And for the question that we just discussed about, for this one, it's none of the above. So, but how do I know if I can really achieve the speed up? So the good thing about MDOS law is that you can use MDOS law to calculate the maximum available speed up. So let's say you have a portion of F. You can accelerate, you can modify. And well, we want to estimate by doing this modification, what's the maximum effect that we can have? So you just replace the speed up by infinity because that's the biggest speed up that you can ever get. And if you did some math, you will figure out it's going to be 1 over 1 minus F. So this would help you to see if we can get the desired speed up. And for the previous question that you guys just discussed, if you use the first corollary of MDOS law, you will figure out, well, after having the flash, even though I have a faster new memory technology like Intel's 3D crosspoint that can they say they call it like optimum memory, right? If I have that, right, and it says I can achieve twice speed up on loading maps, or say like it can achieve like 100 times speed up on loading maps when we are accessing the storage device, it turns out that it can only translate to at maximum of 20% of the 20% of the performance gain, and twice is not possible, right? It's not possible, right? So that's the speed up, right? That's the maximum available speed up. So on the other hand, right, if you have a manager, right, and well, he is giving you like some kind of task saying that, well, like say, well, Nick, well, today I want you to have a task. Our company saying that, well, we want you to spend your a month. Try to speed up the 16% of the time to see if we can achieve twice speed up in the resulting application, right? Then you know that the message behind your boss is asking you to resign because that's never possible, right? So that's the implication of the first corollary. And another implication that we can learn from we can further extend from the first corollary is this. So we said we can apply MDOSL on multiple optimizations. So if we have 4 different disjoint MDOSL optimizations, supposedly, well, we can see like, and if we can only pick one, right? If you can only do one thing at a time, right? If you can do one thing at a time, right? Then which one should I focus on, right? So then the solution is also, let's try to use MDOSL, right? So if you can use MDOSL, then you will figure out that we can get the maximum speed up of each part and choose the one that will give you the minimum speed up, maximum speed up, right? So the second corollary coming from here is that the MDOSL is actually a law tells us that try to spend your time in your effort in the most time-consuming part, or say try to make the common case fast. And when we say the common case here means the part in your program that spend the most amount of time, rather than the code with the longest line of the code, or the portion with the longest line of code. No, none of this, right? It's all by time, right? So that's the second corollary, right? So so you might have a question, right? Like, if I have no knowledge about what's going on in my program, then how can I identify the most time-consuming part? So if you have ever used gprof, right? It's a tool that's in your that's associated with GCC. So if you have a system that already has GCC, it's very likely you are already having the gprof. So and with that, well, so for this program, right now you can see when I compile the array sort, I do have the -pg flag that's already turned on. So when I run an instance of that, it also generates a profile in the meantime. So then with that, by using gprof and your original program and the gmon .out, which generated from there, you can get an input. Well, gmon.out. Yeah, what's wrong? Okay, you can get an output like this, right? So, boy, so I want a shorter. Okay, so this one actually. Okay, so let me try array sort 1. Okay, oops, array sort 1. What's the first argument of array sort 1? Oh, I already changed the program. So array sort 0, and the second argument would be saying, okay, so when I run this program, okay, and I run it with 1. Okay, so when I run this program, right, it will, in the meantime, generate a Gmon dot out like this, right? So then you can use gprof, and it will show you, wow, this is a detailed information about what's going on when you are running that program. So this is probably too hard to digest. So let's try to do, to see what's going on here. So if you go to the very beginning of the code, it will tell you, wow, how much time you spend on each, right? And you will see like a lot of functions that I didn't call, right? But for C++, they do a lot of stuff behind you. So that explains why when we run the hello world, it takes so much effort for the C++ to print the hello world, because they do a lot of stuff implicitly. And but if you look at the amount of time they spend in sort, right? It's actually just this big, right? So it's less than, it's invisible amount of time, right? So sometimes you just think about like, oh, sorting is a lot of effort, right? But for the program, it turns out that, well, something else other than sort is the most time consuming part. So from the algorithm's perspective, you might think about, when I want to improve a program, I should focus on the program that was the highest complexity. But turns out that the highest complexity part only they are actually the least ranking ones in terms of the time consumption. So that's definitely not something you have to focus on. You have to focus on the rest of the thing, right? So that's an implication. And the other thing that you might learn is you need to be aware is that the most time-consuming part is actually a moving target. It's a moving target, so it changes all the time. So so say like this is say in the original program like this, right? We spend a lot of time on CPU. So a lot of people thinking about algorithm is the most important because they think your application always spend a lot of time in computation, right? However, well, thanks to the effort, a lot of algorithm designer, a lot of programmers, or even computer architects, because we make the computer CPU or GPU a lot faster. So it turns out that if we keep improving this like CPU part, eventually it will be really, really small. But the problem that you keep ignoring will become more of an issue. So now I'm giving you another demo to give you some idea about what am I talking, what I want to tell you here. So so for here I have well, we just talked about sorting, right? So here I have an example which I use CPU to implement quick sort, and for this CPU program, it's queued like this. So first of all, I have a CPU version of this hybrid sort, but internally it just does quick sort, and this file is actually on the hard disk drive, and I'm sorting 300 million numbers. So to sort 300 million numbers, it actually takes a lot of time. First, you have on CPU, because first of all, you have to get the file from the hard disk drive, which would take about 10 seconds, right? And and now if you try to sort this huge amount of numbers on CPU, well, because this is like 300 million, so it's a huge number, and it's such a huge number that when you want to sort it, it takes a lot of time that even your lecturer doesn't know how to fill the rest of the minute before it finishes, right? So it's really, really long, and I'm not sure how long is it, but I can tell you this is the latest. Well, this is a nice generation of Intel processor, a Core i5 6-core processor. And even with that kind of processor, a very expensive processor, see, it cannot finish the sorting within a minute, right? So, well, so that's why your algorithm teachers spend a lot of time teaching you the best sorting algorithm, because if you want to do it on CPU, it's really, really slow. And it's so slow in a way that I start to doubt if it will finish. Oh, it finished, right? So the execution time takes about on CPU, the kernel on CPU takes about a minute, 63 seconds. So right now I'm giving you another demo. So a lot of you know GPU, right? So this version runs on GPU, but still have the file on your hard disk drive. So with GPU accelerate sorting, and the sorting algorithm used on the GPU is not quick sort, is actually bucket sort. So with that, right? So see, the hard disk drive access time doesn't get changed. It's still 10 seconds. However, the GPU part only takes about 1.2 seconds to finish. So it's about, I would say like more than 100 times fast. Well, it's about 60 times faster on GPU, right? And another implication that you see here is that previously the CPU sorting is the critical path. You spend majority of time on there. But after you use the GPU, now the most time-consuming part is accessing your hard disk drive. So if you really want to make your performance better significantly, instead of focusing on this part, you should try to move your stuff to a solid state drive like this, right? So with a solid state drive, now you see the performance of file input is shrinking to just 2.3 seconds, right? And it gives you about like 3 times speed up for the total program. So this demo tells you that, first of all, although we should try to focus on the most common part, but the most common part changes over time. It's a moving target, and as long as you keep like using some stuff, then to optimize that, it will change. It will change, right? So that's the implication that you should learn from MLOSL as well. So another thing, right? When we focus on the non-common part, sometimes we think about like for those non-common part, doesn't matter, right? So look at this, right? So if a program spends 90% in A, 10% in B, and assume an optimization can accelerate A by 9 times but hurts B by 10 times, right? So if this is the consequences of that, then what's the new execution time? So let's look at that, right? So the new execution time will become, well, 90% of the old execution time can get a speed up by 9 times, but 10% of them will get slowed down by 10 times. So it turns out that the new execution time is 1.1 times more than the old execution time. So the speed up is actually 0.9, means that you get a slow down. So that's another implication. So sometimes you think about like, okay, there is some overhead when I apply an accelerated computation. However, make sure that overhead is not going to kill you. So one of the examples that I just showed about GPU is that because GPU is external to your CPU and main memory, so you have to copy stuff over the GPU before you can apply your optimization. So the stuff is that if your optimization is not significant enough, but the overhead, additional overhead is a lot, then using GPU is not going to give you any benefits. So that's another implication that you should learn, right? So another thing, some of you might ask, why am I not using MLOSL here? Is because that's a very important thing that I want to point out again. MLOSL doesn't bound slow down, and it doesn't consider overhead like this. So it always assumes that when I apply to an optimization to F, there is no additional overhead. So that's another issues that we have with MLOSL. All right. So another thing that we love about MLOSL is that it helps us to evaluate so we know we have a lot of multi-core. In the very first lecture, we talked about multi-core processor, right? So how can we estimate the maximum benefit from using multi-core processor? So let's say like if I have a program that F portion of the program is parallelizable, so you can easily estimate the maximum benefit of applying n cores, n number of cores on this program would be 1/1 minus f parallelizable plus f parallelizable over n, right? So right now I have a question for you, like using this corollary, can you answer the question below? And this time I sent out a screenshot of this question through the chat. So if in case we need to go to the group chat, make sure that you open the screenshot before you go in there so that you can see the question. But right now is the time for individuals thinking. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so seems like we really need a group discussion. So why don't we go ahead and have you guys discuss in small groups? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now I want to invite some of you to share your group's thoughts, not your thoughts, with us. So who would like to share? Okay, so I have Byron. What do you think?
So for our group, we thought 1 and 3 were the true statements. So for number 1, we weren't exactly sure, but we thought that like I guess if everything is unlimited parallelism, then you'll be slowest by, or the performance will be determined by the slowest piece. Then single core performance does matter because we don't want it to take forever.
Right. So that's exactly this, right? So if you have unlimited parallel hardware units, the single performance still matters, right? Because your speed up is essentially going to be 1 minus f, right?
Yeah.
1 over 1 minus f. Oh, well, yes. Right?
I mean, that's like similar thing for number 3 as well. And then for number 4, the scheduling overhead would be quite major. Like for an example, maybe like reversing or doing something with an array. You would need to schedule it so that you're not doing data racing between elements.
Okay, so it means like other places becomes important too, right? So, so that's why yes. So first of all, right? So if you have unlimited, so first of all, if you have unlimited parallelism, right? So because if you have unlimited, right, and this part is really, really, really large and make the whole f over something becomes not seeable, right? So so means that it also means that the eventually your speed up is going to be 1 over 1 minus f if you have unlimited parallelism. So then the single core performance does matter because this 1 over f is the only stuff that oh, thanks, Byron. So that's the only stuff that that we cannot optimize by parallel processing, and only single core performance can help it, right? And with unlimited amount of hardware units, the maximum speed up will be bound by the fraction of parallel parts that's exactly the same, and that's exactly the split side of the 3. So the 3 is correct, and the first is correct, right? So this question, we got 2 of them that are important. So if you look at this, right, it actually gives us other corollaries. So first of all, right, if we have unlimited parallelism, it means that your speed up is essentially 1 over 1 minus f parallelizable part. So it tells us 2 things. Single port performance still matters because it will eventually dominate the performance. But remember what the video that we keep playing before the lecture, what David Patterson said. He said like, well, single core performance, the future is parallel. The single core performance is not going to improve anymore, right? So if that's the world that we are landing with, so finding more parallelizable part is more important. And another thing, right? Because the parallelism is so large, the complexity of each piece in a parallelizable part is not that important. The complexity of each parallelizable part is not important. So what that tells you, so if you can find enough parallelism, if your hardware is able to extract tons of parallelism, computational complexity, the big old notation of algorithm doesn't make any difference. It doesn't help you improve performance. Did you see that? So this is, well, in other words, if you live in a world with unlimited parallelism, algorithm, the complexity who cares? It doesn't translate to performance, right? So that explains one of the demo that I gave you, Betonic sort. It's n log square n, order of n log square n. But because you can use GPU, you can fully use GPUs with Betonic sort. So the speed up, the scaling is more effective than quicksort, merge sort, whatever algorithm that is n log n. And another thing, some of you might have heard MapReduce. It's the most widely used data center, the most widely used data center computation, data analytics framework. So everything, almost every cloud service that you are using for now, a lot of them are backend is powered by MapReduce. So MapReduce, if you look at the algorithm of MapReduce, they are usually like very stupid, or well, sorry, I shouldn't say the word stupid, very intuitive algorithms that are not really highly optimized by just remap something to something and try to reduce it and just do a lot of simple like calculation without fancy optimization on the complexity. But the truth is that it works a lot faster than the a fancy algorithm on a single core, and a single core algorithm that may not be parallelizable. So instead, so this is the really important. This is the most important implication here, and this is the word that the truth I want to let you guys know, right? The future trend, because we are the hardware is changing. Instead of we are making faster single core processors, we are making processors with more and more cores. So instead of designing your algorithm in a way that try to lower the big O notation in the complexity, making your program more parallelizable is more important than the computational complexity. Is more important than the computational complexity. So this slide is basically telling you like how useless your CSE100 and 101 is. So let me give you another thing about like how many cores, how many parallelism are we having now? So this is a GPU. So for a GPU is basically a collection of string multiprocessor. And so this is like a very early generation of the NVIDIA. I think it's a Pascal generation, which is probably 2 generations ago, right? It's even with Pascal, that's a very old generation GPU, right? Each string multiprocessor is essential. Well, each GPU contains 13 string multiprocessor, and each of the string multiprocessor is essentially 192 slow single cores. So you can imagine that in your GPU is actually a processor with 2,000 cores. So if you can find an algorithm to parallelize across the 2,000 cores, it's going to be more significant than having an algorithm that lower the complexity by like, let's say like half of the order. However, it cannot be parallelized, right? So that's one thing that I do encourage you to seek for as when you become a system designer, an application designer. So the very, very important takeaway here is that the future is parallelism, is parallel. So the future is parallel. So don't be too sticky around your computational complexity. If you are seeking for performance, parallelism is more important than complexity. All right. So that's the important message I want to give you. And right now, we want to talk about, well, so when we talk about performance, in many cases, because we want to compare. So, but to compare, we also need to make sure that we give designs a fair chance to compare each other. We want to design a fair game. So how to make the comparison fair, right? So one of the things that I want to say, right? A lot of you have seen a word, T-flops, in game consoles. When you are buying game consoles, when you are as an intensive gamer, you must saw this a lot, right? So this actually graphs. So this part is actually the most the T-flops of the most popular game consoles, and I made this a table. So like the Nintendo Switch. I have one. I believe a lot of you probably also have one, right? It has 1 teraflops. It means like the T-flops means like the tera floating point operations per second, right? It has 1 teraflops. And I have an older generation of Xbox One, which is already like 1.3 teraflops. And the later generation of Xbox One X, it actually got optimized to 6 teraflops. And PS4 Pro, well, a lot of diehard gamer, they think, well, PS4 is, well, one of my best friend. He always ditched the Microsoft or Nintendo solutions because he think being an intensive gamer, he should have a PlayStation, which I don't agree with that. But but if you think about like the most diehard gamer they are looking for is actually a game console with only 4 teraflops. But if you are a gamer who think the best gaming machine should have the best T-flops, then what really surprises you is that if you have a PC, if you have a GTX 2080, you beat all of the above in a way that the GTX 2080 has 14.2 T-flops. Did you see? But when you play games, right, do you ever feel the T-flops reflect your gaming experience, right? A lot of you would probably say no, right? So why is that? So if you look at what is T-flops, it's defined as the number of floating point instructions times 1 over a tera divided by execution time. So what does that mean? So if you look at the equation, right, it's actually the instruction count in your original program times the percentage of the floating point instructions you have times 1 over a tera divided by the execution time, which is the instruction count times the CPI times the CD, right? So what really happened is that instruction count is gone, right? The instruction count is gone, right? So with the T-flops, every factor that's related to instruction count is gone. So if I have an instruction set architecture that can that generates more instruction count, then that instruction count is gone, right? Although the more instruction count would actually give you longer execution time, right? So everything that is about instruction count is gone. So that's the issue. That's the issue, right? That's the issue of using T-flops as your metrics, because it doesn't tell you if you have a better programmer, right, you can make the performance better, right? It doesn't tell you if you have a better compiler, you can make the performance better. It doesn't tell you if your architecture has lower CPI, but even though it gives you more instruction count, it may give you better performance. So those are the things that's hidden by T-flops. Well, for some reason, I keep thinking about flip-flops today. Well, this is not CSE140, all right? So T-flops is not a fair comparison metrics in this way, because as we said, if you want to evaluate performance, instruction count, CPI, cycle time, they must all be presented in your comparison to make a fair comparison. Okay, so another thing I want to talk about is that, well, there are many people, so I feel like those companies who produce GPUs, they are the guys who knows how to use similar stuff like T flip-flops to fool every of you, right? So for NVIDIA, we know it spends a lot of time telling you like how good we are in AI training, and it tries to tell you like, okay, we can achieve like 100 teraflops. But what it didn't tell you is that this 100 teraflops only works out when your floating point is on 16-bit floating point. So if you have an algorithm that really requires high precision, that's higher than 16-bit floating point precision, because thinking about like how big a 16-bit floating point can express is actually lower than 50. You can only precise the value that's lower than 65K, right? It's a pretty small range of the numbers, right? So if you have anything that's upper than that range, then this flops doesn't work for you, right? So so using that to say, well, we hit like 100 T flops, that's not a fair game, right? So another thing, right? They try to tell like GPU is the best AI hardware, and in the meantime, there's something called like TPU from Google, right? So when they try to tell you why the GPU is a better one, they try to tell you because we can do more inferences per second, right? But again, it's probably not too hard for you to imagine what's wrong with inferences per second, because what model are you used to do inference? What kind of data set are you used to do inference, right? So there's no standard saying how to measure inference per second, right? So that's why benchmark is very important. So in computer architecture, in computer science, in computer systems, if we want to make a fair comparison, everybody has to run the same benchmark, use the same data set, and to make sure that we are setting up a fair game among different computer system design, right? So previously AI wasn't that a big deal, but these days, because people really care about artificial intelligence, so a lot of companies are thinking about like setting up benchmarks for characterizing like AI applications or AI systems. So for example, like Facebook, they start to have this ML perf. Okay, so given we learned this, I want you to relate that to your want to relate to what you have learned to your everyday life beyond this spec that we talk about. So why don't we just watch this video, and I will let you guys, and after watching this video, I will let you guys discuss and tell me what do you think, what's going wrong in this video. Okay, so what this video is trying to tell you that Qualcomm Snapdragon processor is better than their competitor, which obviously is an Intel processor-based laptop. So why don't you spend some time in your small group and tell me about like, okay, if you just, do you trust it? And why don't you trust it? All right, so I believe everybody should be back. So can some of you summarize what's going on in your group discussion and tell me what you guys think? Summarize your group. Well, if not, then let me see. Like, okay, so I have, so Debbie's song, you are the representative of the group in Newer College. What do you think? Are you wrong? Hello? Okay. Hello? Okay. Well, so maybe Jamie's song, what do you think?
We rewatched the video and we actually didn't reach any conclusion.
Okay, you didn't reach any conclusion. But do you remember any discussion in your group?
We were discussing whether we should trust it, but
Okay. So let me see. Okay, Byron, what do you think? Hello? 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 Hello, what do you think?
Oh.
What does your group think?
Our group thought that it wasn't a good representation because the different, maybe the processor is better at doing I don't know, like opening applications and this.
Okay, so
they're
the right set, right? The right set of applications, right? So that's the benchmark programs, right? What else?
And I guess also now that you've mentioned the dual 4K external monitors, that's very GPU heavy as well. So there's other things that are not dependent on the CPU.
GPU heavy, right? So it's not related on the CPU, right? What else?
Also, there's multitasking 7 different applications. So maybe it's better at multi-core performance, but not good at single-core performance.
Right. So there are so many things that it's missing here, right? So first of all, what's a competitor, right? And what's the clock rate of the processor? Like even Intel processor, we can pick like just one processor and we try to set a clock to be just 1 gigahertz, right? And what generation of the Intel processor? How many cores, as you mentioned, right? So those information are missing, right? And how big is the RAM? Like if you have Firefox, well, like, okay, they use Firefox here, right? But how about Chrome? Because Chrome is very RAM consuming, right? And how fast is the disk? Can I have maybe they are using a hard disk drive, a conventional hard disk drive for the competitor's computer, right? So those information are missing and saying Byron. So that's not a fair comparison in this way, right? Okay, so last topic I want to talk about is this. And because of the time limitation, I'm skipping the question on this side, but actually it's very important for you, the difference between latency, throughput, bandwidth, because that's one of the very big misunderstanding in many of the computer engineers. So latency is the amount of time to finish an operation. So when we say execution time, that's like latency. When we say access time, like retrieve something from hard disk, that's the access latency. The response time when you touch your mouse and your keyboard, and by how much time you will receive your response, that's latency. And throughput is the amount of work that can be within a given period of time on average. So sometimes, well, when you purchase the the cable service, they will tell you the bandwidth. And when you purchase the solid state drive, they tend to tell you the IOPS. When you purchase the GPU, they will tell you the T-flops or M-flops, right? So that's all throughputs. So what's wrong with that? So let me give you just one example, and hopefully that will give you some idea about like what's the difference, right? So, well, once in your life, you must have some good friend that always like have a lot of interesting videos in his hard disk drive, right? And for those videos, it's going to be like terabytes or petabytes of them that it's almost impossible to get those with the network. So let's say if we can improve the network technology, and we have 100 gigabit network, and 100 gigabit network means that you can transfer your data 12.5 gigabyte data per second. If you have 2 petabytes of data, it takes about 2 days. However, in terms of watching movie, you can start watching a movie as soon as you have a friend, right? However, well, if your friend is luckily in let's say like 100 miles, so probably somewhere in Irvine or Inland Empire, right, Riverside, right? Then if you drive your Prius on like 75 miles per hour, well, if there's no cops surrounding you, right, then it takes about like 3.5 hours for a round trip, right? And then the max load of this Prius is actually allow you to put like about like 3,000 hard disk drive in there. And assuming that we buy the cheapest one, which is like a 2 terabyte per drive, you can actually get you can actually have an equivalent bandwidth as 290 gigabyte per second. However, right, you will not be able to see anything within 3.5 hours, right? So this example tells you, right, depending on your application, some applications we do want, like watching movie, right? I do want to see the movie as soon as possible. Then using a Prius is not a good idea, right? But if your task is something that you can wait, then turns out that, well, using the network is probably not the most efficient way. If you really want to get the data in the most efficient way, then probably using your car is going to be more efficient than other options. So that's the difference between latency and throughput. So for the latency, it's the round trip time of a single task, a single piece of the big task. And for bandwidth is the average throughput, or say the average amount of time to accomplish a group of tasks within a given period of time, right? So so like this, right? You accomplish the task for about like 3.5 hours, and the bandwidth is 290. But before your car comes back, there is no way you can see anything. So that's the difference between the latency and throughput. Okay, and sorry for the fluctuation in the very beginning, and we are able to finish the lecture on time. So we have a reading quiz on processor design due tomorrow, and is already online, I believe. And make sure you finish that before the lecture tomorrow. And tomorrow we are going to start a new chapter on the processor design. And if you really want to annotate on the slides, I will put the version of the slides without questions before the lecture. Other than that, I will see you tomorrow.